A Softek IT Consult.
Hello, and good day to you, and welcome back to lectures on discrete structures or discrete mathematics, depending on which course you are doing. This second series, remember in our first series, we looked at the introduction to this course, we looked at algorithm, and then we took time to look at some exercise in algorithm. Now, based on our course online, the next thing is to look at logic. But I want us to revisit some aspects of number system. So this series is going to cover basis and number basis, how to convert from one base to the other. And then we'll look at some exercises related to number-based conversion, both positive and negative values, including fractions. And then finally, we'll look at one application to this number system. That's its usage in how to encrypt and how to decrypt information. Definitely, this will be the outline for this series. So I'm going to share my PowerPoint, and then we'll take it from there. Okay, so like I said, the first part is to look at or remind ourselves of how to convert numbers. And first of all, we are going to look at the simple base 10, then we'll look at base 2. Base 10 is also known as the decimal base. We'll take an example of base 8, and then base 16, which is used or normally called the hexadecimal base. Okay, so this is the outline. Now, first of all, let's find out which systems we are interested in. I already repeated that we want to look at various basis conversion. So, but to do that, we need to understand what we call the number system. Okay, so the numbers, when you are giving a number, what do we call the positional value of the number, and then how to be able to convert from one base to the other. Basically, that is what we'll be doing in the first part. Okay, so why are we interested in this at all? Now, if you are offering computer science, or you are information systems or information technology, whether degree or diploma, what computers does is to store information. And computers store information in what we call the binary digits. So we need to understand the concept between how numbers are converted into binary. Now, the other bases that we're interested in, like base 16, one of its application is how to use it to represent a convenient way of representing information. Very soon you realize that as the numbers we are converting becomes very large, hence the conversion to base 2 also becomes very, very long, and it will take what we call the memory space. So hexadecimal and other types of conversion is resorted to be able to represent this information digitally. Now, so this representation is one of its important. The other thing is it helps students to interact more with the way computer or computing programs or courses are like. It's a career you have chosen, so you need to be familiar with this. Now, so first of all, let's revisit how this is done. So we want to revisit what we refer to as exponent numbers. If you did call math, you should be very familiar with what exponents are, or the powers of a number. Now, in the first place, anytime you raise a number to a positive number, it means you're multiplying it by the number of times. So 3 raised to the power 3 means 3 times 3 times 3. I hope you are familiar with this. And if you raise a number to 0, everybody knows that that number becomes 1. Okay, lots of indices. But if you raise a number to 1, then the number becomes itself. Now, the fourth point is that any number raised to a negative power, it means we are finding what we call the reciprocal. So the number becomes a fraction. Remember, in my introduction, I said we'll be looking at number system, both positive and negative, including fractions. So we want to look at the negative part of, or what we call the fractional part of a number. So we need to know when a number is raised to a negative power. Okay, we'll take examples to explain this further. If you've forgotten, or we'll sort you out as we go on. Okay, so let's now revisit some terminologies. First of all, when you say base 10, which you refer to decimal base, it is the most familiar number that you should be aware of, because from KG, when you started learning how to write, all the numbers you wrote are actually base 10, because you wrote from 0 to 100, and then now you can write in any number at all if it's mentioned. All those numbers are called base 10 because it's made up of digits from 0 up to 9, either in single digits or in combined digits. So 100 is a digit 1, a digit 0, and a digit 0. But when you say base 2, which is what I said will be preferred, we'll be looking at, is actually made up of 0 and a 1. Now, when we say base 8, then we are looking at numbers from 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7. And then when we refer to base 16, then we are looking at numbers from 0 to 9. Then the digits 10, 11, 12, 13, 14, 15 is represented as A, B, C, D, E, and F. Okay. Now, when we say base, the base of a number, what it means is that we are going to take every number we write divided by the base and take the remainder. So when you say base 2, then it means that we are going to divide the number by the number 2. The remainder we get is what will represent the number. I will show you on my Excel page more of this example. So let's do more of intro to this. Okay, so first of all, we will take a number in base 10, find out the position, or what we refer to as the positional values, this positional value, and then we'll be able to find out why it is referred to as base 10. Okay, so for example, this number 3456.123. Now, if you look at the number 6, the positional value of the number 6 is in the position of ones. I hope you know ones, tens, hundreds. So when you say ones, it means you are raising the digit to the power 0. So it means that 6 has a positional value of 0. And number 5 is the second from the right. That's the whole part of the number. Okay, it's in the position of 10. What is 10? It's 10 raised to the power 1. So it means that we are raising the position, or the position of this number, as 10 raised to the power 1, or as a value of 1. The third number from right is 4. Now, 4 is in the 100. What is 100? It's 10 raised to the power 2. So it means that the position value of the value 4 is 2. Then the fourth number is 3. It's in the position of 1,000. It means that this is 10 raised to the power 3. That is 1,000. Now, when you come to the fractional part, or the decimal part, the first digit after the decimal point, the decimal starts from 10 raised to the power negative 1. It means that will give you 0.1. The 2 is 10 raised to the power negative 2. That will give you dividing by 100. 3 will be 10 raised to the power minus 3. It means you are dividing by 1,000. If you are forgetting these indices, I will recommend, please find a calculator and revise these things, because we'll be applying them as we go on. Okay, so we want to pick the names of what we call binary digits, base 2. First of all, the word biny or bini means 2 by 2. So when we say base 2, we are saying we are picking 2 at a time. And I've already told you that base 2 is made up of only 2 numbers, 0 and a 1. Now, the symbol in this system are often referred to binary digits. Now, very soon you realize that the method in which we store information is called bits. B-I-T-S, bits. Okay? So when you buy a phone, it says I have this megabyte or this gigabyte. The basic unit is bits. How do we get that name? It's from the word binary digits. I've already told you that computers store information using what we call binary digits. So the storage size of any storage system, like a pen drive, like an external flash drive, or a CD-ROM, all these things are in the size of gigs, megabytes, kilobytes. I'm saying that bit, B-I-T-S, is coming from the word binary digits. The B, that starts the spelling of binary, and then the ITS that ends the spelling of digits. Is how the name bits was derived. Okay, well, this is just for history's sake. Nobody's going to test you on this, but basically that's how the storage, minimum storage size of any external drive or storage of any system you use are virtually named. How many of you remember the first external sort of storage or the first size of a floppy disk? I don't think most of you were born when we started using floppy disks. I'm not too sure. But if you can tell me what's the size of a floppy disk, I think I'll get you an orange. Well, so here we are. Now this is base 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so any number that is represented by 0 to 9, then it's in base 10. Base 2 is 0 and 1. We are repeating our information. Base 8 is 0 to 7. So you see, we from base 10, a number 10, you have digits from 0 and ends at 9. So when you say a base, we will pick digits that are less, up to the number less than itself. So 10, 0 to 9, 2, 0 to 1, 8, 0 to 7. So base 16 will be what? 0 to 15. I already told you that the numbers will be represented by 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the number 10, 11, 12, 13, 14, 15 will be represented by A. Why? Because the number 10 happens to be represented with 2 digits. And we are converting systems into a base. So we don't want to be representing an information with 2 digits. So instead of writing 10, we'll represent it with A. Instead of writing 11, we'll represent it with B. Okay? So a word like FACE, if I tell you it's a base 10, it means that I'm referring to F as 15, A as 10, C 12, and E 14. Okay, we'll see all these examples as we go on. Okay, now we want to now claim or verify why we say a number is in base 10. Some of you, these things will be just familiar with you. When we say 4,202, if I ask you to prove that this number is base 10, what do? It means that take your time and take the number raised to a position. 2 is the last digit. It means it raised to the power 0. So 2 times 10 is the power 0. Okay, then 0 will be 0 times 10 is the power 1 because it's in the position of tens. And then 2 will be 2 times 10 is the power 2 because in the 100th position. And then the last one, 4, will be 4 times 10 is the power 3. It's in the 1,000th position. When you evaluate this, 2 times 10 is the power 0 will give you 2. 0 times anything is 0. 2 times 10 is the power 2 will give you 200. So 2 plus 200, that will give you 202. And then 4 times 1,000 will give you 4,000. So 4,000 plus 202 will give you 4,202. This is why this number is in base 10. Okay. Now, if we claim this number is in base 2, the same thing. Take the number, multiply by the base, raised to the position it occurs. So this is 10011. Do you realize that the digits here are made up of zeros and ones? Okay, that's why we claim this is base 2. So verification. 1 times 3 is the power 0. Again, this 1 is in a position of, let's say, if it were to be, then we say position of 0. We number the position from right to left. So 0, 1, 2, 3, 4. So 1 times 3 is the power 0. The next one, 1 times 3 is the power 1. The next one, 0 times 2 is the power 2. The next one, 0 times 3 is the power 3. And the last one, 1 times 3 is the power 4. When you evaluate this, it's going to give you a value in terms of a base 10. Divide that number by 2 and you get back this. I'm going to explain this further in my Excel. Okay, so there are more examples in my slide. Take your time and work through them. Okay, so just like this one, 10101, when we evaluated it, it gave us 1 plus 4 plus 16. Okay, that gives you 21. This will give us 23. This will give us 35. I'm going to work this out in my Excel. So We'll come back to our application and then continue from there. So let's go to the Excel page and then see how to represent this information or verify this information. Okay, I hope you can see my screen. I'm just enlarging it. So the example we saw a few minutes ago was 10101. I've taken my time, represented this in Excel. So the first digit is raised to the power 0, 1 times raised to the power 0, 0 times raised to the power 1, 1 times raised to the power 2. So let's evaluate this. Okay. Now, 1 times raised to the power 0, 2 raised to the power 0 will give you 1. 1 times 1 will give you 1. Okay. Now, 0 times 2, 0 times any number is 0. So this value will be 0. Okay. Now, when we come here, 1 times 2 is the power 2. 2 is the power 2 is 4. So 1 times 4 will give you 4. Then this, 0 times any number will give you 0. And 2 is the power 4 will give you 16. I hope you know that. Times 1 will give you 16. When you add 1 plus 0 plus 4 plus 16, 16 plus 4 will give you 10, and 10 plus 1 will give you 11. Sorry, am I right? Sorry, 16 plus 4 will give you 20, and 20 plus 1 will give you 21. So there you are. Now we want to verify this, that this is actually based. So now the answer is 21. We have it. We verified it. Now we want to divide this 21 by 2, and we are using long division. I hope you know this method. You are picking only the remainders. Now 2 will go into 21. 2 into 21 will be 10 times 2, 10, 20, remainder 1. I hope you know this. Okay, now then we divide 10 by 2. So we write a 2, we divide 10 5 times, 2, 5, 10, remainder 0. You know that. And then 2 again will divide 5, 2 will go into 5 2 times, isn't it? Remainder 1, 2, 2, 4. And then the last one, 2 again will divide 2, 2 will go into 2, 1, remainder 0. Okay, so when we pick the values from right to left, bottom to top, the value we are going to get here is 10101, which is exactly the value we started with. So we verify that this is base 2. Let's take another example. Okay, so this time we are going to work this thing out ourselves. So here, first of all, look at the position of the digit. This one will raise the power 0. This will be raised to the power 1. This will be raised to the power 2. This will be raised to the power 3. This will be raised to the power 4. So let's do that here. So the first one, 1 times 2 raised to the power 0 plus 1 times 2 raised to the power 1 plus 1 times 2 raised to the power 2 plus 1 times 2 raised to the power 3. How many ones have I done? I think this should be 0. The third, 1, 1, 1. The last one is 0. 0 times 2 raised to the power 3. And then the last one, plus 1 times 2 raised to the power 4. Now, let's come here and evaluate it. Now, 1 times 2 raised to the power 0. 2 raised to the power 0 will simply give you 1. 1 times 1 will give you 1. Now, let's come here. 1 times 2 raised to the power 1. 2 raised to the power 1 is 2. Times 1 will give you 2. Here. 2 raised to the power 2 will give you 4. 0. 2 raised to the power 3 will give you 8. 8 times 0 is 0. And the last one, 2 raised to the power, what did I do here? 2 raised to the power 4, I wrote 6. Now 2 raised to the power 4 will give you 16. Again, when we add this up, 16 plus 4 is 20, 22, and 23. So now we are verifying 23. That's what I have here. Let's verify. 2 into 23, we'll go there 10 times. 2, 10, 20. Sorry, 2, 11, 22. Remainder 1. Now 2 into 11 will be 2, 5, 10. Remainder 1. 2 into 5 is 2, 2, 4. Remainder 1. And then 2 into 2 will be 2, 1, 2. Remainder 0. And if you take your time and pick from left to right, top to bottom, left to right, top to bottom, we end up getting 1, 0, 1, 1, 1, which is exactly the value here. Okay, I hope if this is the first time you're seeing this, you should be able to do this. You should know how this is done. So this is how we verify base 2. Okay, there are quite a number more we could try. There was 35. I think that's what I wanted to write, 35, but I'm going to leave that for you to try. Okay, so now we want to verify base 8. Okay, base 8. Let's assume that this number is 27. 27. We want to verify that 27 is a number in base 8. I've already done that. First of all, remember the number is made up of 2 and 7. So if I pick the number 7, I will raise it to position 0. Remember, we start finding the position of the numbers. So 7 is the power 0. So 7 times 8 is the power 0. The base is 8, so we'll be multiplying by 8. Plus 2 times 8 is the power 1. When you evaluate this, 8 to the power 0 will give you 7. And 8 to the power 1 will give us 8. 8 to 16. 7 plus 16 will give us 23. Again, let's verify. 8 divided by 23 will give you simply 8 into 23 is 8 to 16. Remainder 7. That gives you 2, 7, which is exactly the value we started with. Okay? So this is base 8. You can pick any number and go through the same procedure. That will show that the number is in base 8. Now, then I'm going to take an example in base 16. This is a little bit involving, but I've done part of it. Now, I'm claiming, remember I told you that a base 16 is made up of, first of all, it's made up of 0. It's made up of 0, 0, 1, 2, 3, all the way up to 9. Okay, then followed by A, B, C, D. So if I give you a value like BC12 or BC12, and I'm asking you to verify that this is base 16, what are we supposed to do? Again, starting from the back, you have 2. So 2 times the base is 16. Okay, 2 times 16 raised to the power 0. Now 16 raised to the power 0 will simply give you 1, and times 2 will give you 2. Now then 1 times 16 raised to the power 1, that will give us 16 here. Then C, what is C? C is 12. So 12 times 16 raised to the power 2. 16 raised to the power 2 will give you 256 or so. Multiply by 12 will give you 302. And then the last one is 11 times 3 raised to the power 3. That will give you that. So when you add 2 plus 16 plus 302 plus this, it will give you a value 48,146. And I know this is because of time, but take your time and go through what I have done. We are now using long division to divide these numbers. So to verify that this base 16, again, 16 will go to 4814. Take your calculator. You realize that you get 3,009, remainder 2. Okay? Then 16 into 3,009, we get 188, remainder 1. And then 16 into 180 will give you 11, remainder 12. Now, so we are picking this from left to right, bottom to top. What is 11? 11 is B, you see it here. What is 12? The number 12, remainder 12. 12 is C, so you see BC. And then we have 1, 2. So this is why this is base 16. Okay, I'm going to give you quite a number of exercises which you can do to be able to be very flexible or comfortable with how this is done. Okay, so I'm going to go back to my PowerPoint and then we'll continue from where we left off. Okay, now we are looking more at why are we doing all this application to this. Now, we first of all, any digital system that has two states, for example, your laptop, you can on your laptop and you can really switch it off. This is because the laptop can work between what we call on and off. In binary digit, we say 1 is true, 0 is false. And hopefully next 2 weeks, we'll be looking at this. So any system that can behave like 1 and 0 or on and off is a binary value which has only two states. Now, when we take our time and add 8 bits, it gives us what we call a byte. This collection of these bytes gives us what we call a collection of a word. So a word that we form, these words you are speaking, if you are representing it digitally, it's actually zeros and ones which have been combined. Then we have bytes, okay? Then the next time we're talking about kilobytes, we're talking about gigabytes and all that. So a word is a collection of bytes, a nibble is half of a byte. Okay, so these are terminology you should be familiar with. So in the gist, if you take your time and convert basically numbers, okay? 0, 1, 2, 3, 4, 5. If you divide them by 2 to be written as 0, 1, 10, 11, 10, on and on and on. And then when we get to 10, 11, 12, 13, 14, 15, 16, 17, 18, down there, then they will start giving us 4 bits or zeros and ones, so it's made up of 4. Then we come to 5, we go to on and on, then they start increasing. Okay, so all we are saying is that numbers can very easily be converted to binary digits, especially base 10. Okay, now, but the way this is taking storage space, we have to find a more convenient way. Now, in base 10, we are just at 36. When we were looking at the number 0, the number of bits we were getting was just 1 digit. By the time we got to the number 2, we are using 2 bits. I hope you understand what I mean by bits. The 0 and the 1s, 2 bits. When we got to 4, we were now in 3 bits. When we got to 8, we were in 4 bits. Now, when we got to 16, we were in 5 bits. Now, look at this. When we get to 36, we are in 6 bits. So there are a number of digits that the binary conversion was doing or was using a storage space, and it was increasing in the number of zeros and ones that we are having. That's what I'm calling bits. So there must be a more convenient way. What if I ask you to convert the money in a World Bank, all the money in the World Bank, okay, the digits, not the digits, the value, convert it to base 2. When I start dividing right now, I'm sure I'll go back and you go for lunch and come back and so we'll not finish dividing. So that means that converting this into base 2 will be a zeros and ones, a long line of zeros and ones. And this is going to take storage space. So, well, people sat down and came out with a more convenient way of representing this. We call it what we call the binary coded decimal. So I'm going to skip through some of this slide and talk about what we call BCD. A BCD is what we call a binary coded decimal. What it does is that it will pick every digit in base 10 and convert it to a bit of 4. So for example, the number 14, 1, 4, it will convert the number 1 into a base of, in a bit of 4. So first of all, convert 1 to base 2. You know 1 is just 1 in base 2. So to leave it in a bit of 4, you add zeros in front. I will show you in my Excel page. Then we'll take the number 4, convert it to base 2. You divide 4 by 2, the remainder is pick it. Now, you realize that 4 will give us about 2 digits. Okay, 2 digits. So to convert it to a bit of 4, we add zeros in front. So this is how we represent binary digit. This is what I'm saying. A binary digit would pick the value 0 to 9. Remember, 0 used to be just 0. 1 used to be just 1. 2 will give us 10. So to make up 4 bits, we add zeros in front. Okay, let me take you to my Excel page and explain this better. Okay, so we are back here. Now, so I'm saying that what BCD does is that it will pick the number. It represents a bit of 4. So this is where the numbers are. Now, so I started by just picking 1 in base 2 will just be 1. Now, 2 in base 2 will give us 10. If you are not familiar with this, it means divide 2 by 2. Now, you know 2 into 2 will give you one whole number, remainder 0. So if you pick the number to 1, 0, that's how we got this value of 10. Okay? If you want to check, how do we do 3? Change this thing to 3. 2 into 3 will be one whole number, 2, 1, 2, remainder 1. So you realize that 3 will give us the value 11. Now let's do 4. 2 into 4. 2 will go into 4 2 times. 2 to 4, remainder 0. Then 2 will come and divide again. 2 into 2 will give me one whole number, remainder 0. So 2 into 4 will give us 100. 100. If you want to try 5. 2 into 5 will be two whole number, remainder 1. 2 to 4, remainder 1. 2 will go into 2, one whole number, remainder 0. Okay, so what is 5? 101. Okay, so I hope you see where we are going. Okay, so on and on and on. You saw in the slide all of this. 2 into 6, 2 into 6. 2 will go into 6 3 times. 2, 3, 6, remainder 0. 2 go into 3, 2, 1, 2, remainder 1. So what is 6? 110. 110. Okay, so I'm going to skip some of this. You can finish up. Now, so what is 10? 10 will be 2 into 10 will be 2, 5, 10, remainder 0. 2 into 5 is 2, 2, 4, remainder 1. 2 into 2 is 2, 1, 2, remainder 0. So what is the value? 1010. So 10 will give you 1010. Let's try 15. 2 into 15 is 2, 7, 14, remainder 1. 2 into 7 is 2, 3, 6, remainder 1. 2 into 3 is 2, 1, 2, remainder 1. So what is 15? 1, 1, 1. Sorry, 4 ones. So you realize that we can take our time and do all this, but for time's sake, you can finish this thing up. Now, I'm now trying to explain what BCD is. So to do that, I must first of all tell you how the computer represents this in binary. Now, it will pick the formula 2 raised to the power n, where n can take the value from 0 to whatever digit. So 2 raised to the power 0 will just give you 1. That's where we have values like 0 and a 1. So 0 and a 1. 2 raised to the power 1 will give us 2 values. 2 raised to the power 1 is 2. So 2 values, a bit of 2. Who wants to store an information a bit of 2? It's not relevant. Okay? But if you want to store 1 in a bit of 2, it means we'll call it 0, 1. But 10 is already a bit of 2. 11 is a bit of 2. Now, a number like 4, this 4, we cannot store it a bit of 2. So this column, we are not so much interested in a bit of 2. The size or the storage size for this is so small. Now, then let's go to a bit of 4. That is 2 raised to the power 2. Now, so this number 1, if we want to express in a bit of 4, add, it means that we are going to add 3 zeros in front. That will give you 0, 0, 0, 1. That's what BCD was going to use. So the number 10, you add 2 zeros in front. So 0, 0, 1, 0. So 11 will be what? 0, 0, 1, 1. And 4 will be what? 4 represented giving us 100 will give us 0, 1, 0, 0. What will be 5? 0, 1, 0, 1. Okay. What will be 6? We got 6. 6 is 0, 1, 1, 0. Okay. What will be 7? If you do 7 here, 7 is 2, 3, 6, remainder 1, 2, 1, 2, remainder 1. So when we come to the value 7, we are going to get 1, 1, 1. So when we come to 7 here, add 0 in front, 0, 1, 1, 1. What about 8? 2 into 8, 2, 4, 8. So 4, remainder 0. 2 into 4 is 2, 2, 4. 2, remainder 0. 2 into 2 is one whole number, remainder 0. So what is 8? 8 will give you 1,000 like this. So already this is a 4-bit, so we just leave it at 1,000. What about 9? If it's 9, we are dividing. 2 into 9 is 2, 4, 8, remainder 1. 2 into 4 is 2, 2, 4, remainder 0. 2 into 2 is 2, 1, remainder 0. So what is 9? That is 1, 0, 1. Again, so that will be 1, 0, 0, 1. So in the slide, you realize that I showed you this. So we'll be able to represent these numbers in a bit of 4 from 0 to 9. Okay, now, so as we go on and the bits increases, 2 raised to the power 3, what are we supposed to do? The same number, these numbers we are seeing here, this base 2, we want to express them in a bit of 8. It means that even though this is conversion of base 2, let the representation of this be a bit of 8. So you add number of zeros to the left or in front so that you can make a bit of 8. So here, that's normal. If we pick this, if we want to represent this as a bit of 8, it means I'm going to add 4 zeros before I will repeat this. 1, 2, 3, 4, followed by 0, 0, 0, 1. So this is this. Then this one is 10. It gave us, that's number 2, give us 10. This is how you represent the bit of 8. What about this one? You add 4 zeros in front, followed by 0, 0, 1, 1. What about this? You're going to have 1, 2, 3, 4, followed by 0, 1, 0, 0. What about this? 1, 2, 3, 4, followed by exactly the value here, this value. That will be 0, 1, 0, 1. So on and on and on. This one word, for example, will be 4 zeros, and then you add, you repeat the value you got for a bit of 4, 1, 0, 1, 0. Okay. Now, so you can continue and do this in a bit of 16. 2 raised to the power 4. I've done one of them. So for example, this one like this. Okay. If I want to get a bit of 16, just pick this. But I'll represent 8 zeros first. 1, 2, 3, 4. 1, 2, 3, 4. And then add, repeat what I have here. This will give you a bit of 16. So if I pick these values, all I need to do is to add 8 zeros in front so that I can get a bit of 16. So this is how the computer stores information. When they say you are downloading something, but it's a bit of 256, a bit of 32, a bit of this is what it means. That number will be represented as that number of digits long. It's because of what the program does. But we realize that as the values were increasing, like we did for 15, it gave us this. When you go to 16, for example, right now, 16, 2, 8, 6, 10, remainder 0. 2 into 8 is 2, 4, 8, remainder 0. 2 into 4 is 2, 2, 4, remainder 0. 2 into 2 is 2, 1, remainder 0. So you realize that you get 10,000. So here, 16, 10,000. Now you realize that 10,000 is made up of 5 bits. 1, 2, 3, 4, 5. It means that you cannot store that value in a bit of 2. You can't store in a bit of 4 because the only place you can store the number 17 will be a bit of 8 going. What is 17? 17 is here. So I'm saying that you can only go and place this value in the bit of 8 here. Okay, so it's 10,000. So it means that already 5 digits have been taken. To make up 8 bits, you bring 3 zeros in front. 1, 2, 3, 1. Then the 4 zeros here. This will represent this value. I hope I'm not on the right row. Okay, so my point is this. If the number, when you divide by 2 and gives you digits that are more than the bit space allocated for it, you move to the next bit. I said we are using 2 raised to the power n. And that is how we get these bit spaces. Okay, now we need to try and wrap up. I don't want this to go so long. So I'm going to go back to my PowerPoint. But before that, let's first of all look at how BCD will do the same thing. Now, what BCD does is that BCD is only interested in the number of digits that is occurring. So a value like 1 will represent it as a bit of 4. So 1 will give you 0, 0, 0, 1. 2 give us 10. Now will give us 0, 0, 1, 0. Okay, so the single digit from 1 all the way out to 9. You realize that when we did it, we were not getting anything extraordinary. Okay, so I'm saying that for those values, we are not really worried about these things. I'm talking about from 1 to 3 up to 9. I'm saying 1 gave us 1, so 0, 0, 0, 1. 2 gave us 10, so 0, 0. I've not formatted this. That's why it's behaving like this. Okay, so this will give you 0, 0, 0, 1. This will give you 0, 0, 1, 0. So a value like 15, which give us 4 ones, will still be like this. Now a value like 16, okay? Sorry, before we get to this. Now, so up to 9, we don't have a problem. The values we got here will be represented the same way as we got there, all these values. So from here to this will be the same as we get here because the values are already up to a bit of 4. Okay, but when we get to a number like 10, what BCD does is that it's going to pick each digit, okay? It will pick the digit. Let me do it this way, then I'll explain. 1. What is 1 in a bit of 4? It's 0, 0, 0, 1, okay? What is 0 in a bit of 4? That is 4, 0, 1, 2, 3, 4. So what we are saying is that this 10 will be represented as 0, 0, 0, 1. Okay, it will be represented as 0, 0, 0, 1 followed by 0, 0, 0, 0. That is for the number 10. Okay. I'm saying that this number 10 will be represented as this. Now, what about 11? So the same thing. 11, 1 is represented as 0, 0, 0, 1. And then the other one will also be represented as 0, 0, 0, 1. So again, so here, we are going to have 0, 0, 0, 1 followed by 0, 0, 0, 1. Okay, so we did 15. 15 in a bit of, when we did 15, we got 1, 1, 1, 1. That is base 2. How will you represent 15 in what do you call it, in BCD? So 1, the number 1 in bit of 4 is 0, 0, 0, 1. And then the number 5 in a bit of 4, what was 5? 5 is 0, 1, 0, 1. So followed by 0, 1, 0, 1. Okay. Now what about 16? 1 and 6. 1 will be 0, 0, 0, 1. And 6, what is 6? 6 gave us 1, 0, 1, 1, 0. 0, 1, 1, 0. So this is how BCD does its things. Okay. Now, so the last part of my my slide, we will talk about how to convert numbers to fractions. So what if you are given a number that has a decimal part? Okay, for example, 0.25. How do you convert that to base 2? How do we do that? Okay, or we have 1.125. How do you do that? How do we convert these fractional part of a decimal number? Okay, so we're going to take care of that in my Excel. So back to the Excel. So these are the numbers. Now what we do is that when you are given the number, we are going to pick the fractional part and multiply by 2. So for example, a number like 0.25, you multiply by 2, 2 times 5 is going to give you 10, okay? And 2 to 4 will give you 5. Okay, so we are going to have 0.5 50. I hope you're familiar. 5 to 10. You write the 0, carry 1, 2 to 4, 5. Now, what we are going to do is that we are going to pick this 0. Okay, that is going to be the remainder. 0 like this. The remainder will be picking. Then we multiply this, the value you got again by 2. So multiply this again by 2. Okay, 5 will give us 2 times 5 will give us 1. Will give us 1.0. Okay, then 1.0. Unfortunately, this is not allowing me to do what I want to do. Okay, then we are going to pick this one and add it to this. Okay, so it means that when we convert the number when we convert a number 0.25 to base 2, we are going to get 0, 1. This is the values we are going to get. You know, remember the first value we got from here. We picked this 0. I shaded this as red. And then here we will take this 1. So that gives you the value 0 and a 1. Okay, now let's try this ones too. Okay, 5 to 10, 74. So this will give you 1.50 when you do this. Okay, so 1.50, what do? We will pick this one. I'm doing the same thing here. So we are saying that 0.75, the first remainder we got was 1. I'm saying we're picking this one. The number that comes before the decimal point is what we pick. That's our remainder. Then we multiply the fractional part, the 0.50 by 2. I multiply here by 2, I'm going to get, multiply 0.5 by 2, we are going to get 1.0. Okay, again, we are going to pick this 1. So you see that the other remainder will give you 1. So 0.75 will give us 1. That is a remainder. Okay, so the same thing applies. If I multiply this 2 by 2, I'll be picking the remainders to give me the values I want. Now, I'm going to leave this one for you to try. So, for example, this 15.25, okay, is going to give you 15. When you convert it to base 2, will give you 111, 4 ones, and then 0.25 give us 0.1. Let's try this and see. 0.75 is giving us 1. So this one will give us, again, formatting. Okay, so it's back. Now, this one is going to give us 1111 points. 0.75 gives us 0.11. Okay, so when you get the value for this one, then it becomes 1111 point whatever. Now, the last part of my slide is to be able to find how do we represent negative numbers. Okay, now negative numbers, there are 3 types. What we do is that we have something we call a sign magnitude. We have 1 complement and 2 complements. Okay, so the first one, what it does is that when you are giving a value, like these values we got here. So I'm coming to the values I got here. This was BCD. Okay, so sign magnitude, make sure that the digits that are in front of your number, there are some extra zeros. So if I want to represent, remember this is 1. In BCD gave us this. Okay, if I want to represent this, let's say in sign magnitude, all I need to do is to change the 0, the first 0 to the left, the leftmost 0, you change it to 1. Okay, this can be found in my slide. You change the leftmost bit to 1. Okay, I want to explain it here, and then we will take it in my next video. Examples in my next video. Okay, so this is what I'm referring to. So I'm saying that negative numbers in base 2 is virtually three. There are three ways in doing them. The first one is that for sign magnitude, all you need to do is that the leftmost bits used to represent the sign. So if the sign is negative, the 0 in front of your number, 0 means that the number is positive. If I change the 0 to 1, then it's negative. So if you remember, a number like 15 gave us 4 ones. If I represent that number 15 in a bit of 8, okay, bit of 8, that would mean that I'm going to have how many 4 zeros and then 4 ones. The first 0 in front of that number, I'll change it to 1, and it will give me negative 15. Okay, so that is an example here. When we convert the number 5, what is 5? 5 will give us 101. If I express this in a bit of 8, 101, it means I add zeros to make up 8. 1, 2, 3, 4, 5, 6, 7, 8. So positive 5 will be like this. Negative 5 is just change this first 0 to 1. Okay, now, so this is all sign magnitude does. It changes the first zeros to 1. Now, hopefully the next video, I'm going to explain how to convert using what we call one complement. But in just what one complement means is that if this is your original value of 5, then every number which is 1 change to 0, and every number which is 0 change to 1. That's what one complement means. So it means that this number, I'll change this 1 to 0, this 0 to 1, this will be 0, this will be 1, 1, 1, 1, 1. That is one complement. And two complements is a little bit, has two steps. It says that if there are zeros to the right, leave it. Leave all zeros to the right. And then the first digit, which is 1, also leave it. Every number left, complement it. So hopefully in my next video, I'm going to take examples on negative values, and then we can be able to know how numbers can be represented as negative. So I'll do that and then add how to apply this in what we call encryption and decryption.
For more information and also to reach us, please contact the numbers on the screen. You can also reach us through our social media handles displayed on the screen. Please do like, follow, and subscribe to our social media handles. A Softek IT Consult. Innovative solutions with the difference.